Hi, everyone. Today we are doing our second lesson in our organized counting unit. We're going to be talking about factorials and permutations. To get started, so a little bit of like maybe warm-up questions or motivation questions. Can you use the fundamental counting principle we learned in our last lesson to figure out how many ways you could arrange the letters in these three words? So math, Asher, and Brighton. All distinct letters. Use the fundamental counting principle. You can pause the video if you'd like and unpause when you're ready, or you can follow along with me right now. So let's do math first. If you set up the fundamental counting principle, you have 4 choices for your first letter, and then once one is used, you have 3 choices for your second, and then continuing, you will have 2, then 1 choice for your last letter. And when you multiply these together, you get 24 different ways that you could scramble the word math. For Asher, the calculation looks similar, except to start, you have 5 letters to choose from, and then 4 for your second, and so on and so forth. This gives you 120. And for Bryden, you must get the pattern by now. 6 choices, 5, 4, 3, 2, and 1. And this multiplies to 720. 720 different ways to scramble the word, the letters in Bryden. Now, these calculations where you take a number and multiply down to 1 are so useful and occur often enough that we give them their own name. That name is factorials. And maybe you've even heard of this before. The definition of a factorial, and this exclamation point here, this is read like n factorial. It's not shouting n, it's n factorial. That exclamation point indicates that. This button can be found on your calculators. It may look like just an exclamation point. It may look like an exclamation point, or possibly X exclamation point. But it's the definition is you take n and you multiply by a number 1 less than that, and then 1 less than that, and you carry on down until 1. So another example would be even a small number like 3 factorial. That means you do 3 and then times 1 less than 3, and then times 1 less than 2, until you get down to 1. 3 factorial is equal to 6. Why don't you guys try applying this definition of factorial to try these? 6 factorial, 9 factorial. You can try them by hand, but I would definitely suggest getting used to that button on your calculator. So find that button. We've already done 6 factorial, actually. I'll rewrite it just for this one. We did it. This is the number of ways to arrange the letters in Bryden. It was 6 down to 1, and that was 720. But make sure you can do that on your calculator. Type in 6 factorial, make sure you get 720, and then try 9 factorial. You're going to see that they start to get pretty big pretty quickly. 9 factorial is equal to 362,880. So now that you've found that button and you're comfortable computing factorials, at times we may need to play around with some expressions a bit and use our knowledge of factorials to simplify some complex expressions. Not so complex, but in this example here, if you actually try to do 108 factorial, like just try it right now. What you're going to see is that, and even for 106 factorial, you're going to get an error message. And it's not that that number doesn't exist. It's just too big to even store on your calculator. How would we evaluate an expression like this? Well, we use the definition of factorial. We can rewrite the top as 108 times 107 times 106 all the way down to 1. However, 106, 105, 104 all the way down to 1, that's just the very definition of 106 factorial. So I can almost peel off those first two, 108, 107, and then write the rest as 106 factorial over 106 factorial, and those divide out, those divide to 1. What you're left with is something you can easily do on a calculator, 108 times 107. 11,556. Using the same logic, we can evaluate an expression like this and try to see a pattern. What do you get if you do a number factorial divided by one less than that factorial? Well, we can write n factorial as n times n minus 1, and then n minus 2, n minus 3, but we can write all those ending ones as n minus 1 factorial. We're using the same trick as before. Divided by n minus 1 factorial. Those divide out, and you're just left with n. That's a pretty neat result. So for example, if you do 10 factorial divided by 9 factorial, you kind of automatically know that's going to equal 10, right? Because you're going to have 10 times 9, all the way down to 1. And then 9 factorial all the way down to 1. And you can see you're just going to left with 10. So in practice, you could do something like 72 factorial over 71 factorial, and you shouldn't really even have to do any work for that. You can just recognize that by the definition of factorials, that's just going to give you 72. Factorials can be useful for organized counting problems. Here's why. So say we have we have a shelf of 10 books. We want to place these 10 books on a shelf. We're going to think, how many ways can we arrange these books? Well, if we were in our last lesson, we would have set up an FCP 5, 6, 7, 8, 9, 10. You can see this is getting cumbersome already. And 10, you do 10 times 9 times 8, all the way down until there's one choice of book at the end. But we can move beyond that now, because we know that that calculation is equivalent to 10 factorial, which we can do quickly and efficiently on our calculators. 10 factorial is equal to 3,628,800. The key idea, takeaway from this question, is that if you have n objects and you're arranging all of those objects, the number of ways to do that is n factorial. So a really useful way to make our counting problems more efficient. So you try this one. A half-hour TV show has 8 30-second advertisement time slots. How many different ways could you arrange those advertisements? How many different ways can you assign them a time? You can pause the video and try that quickly, or follow along with me. Again, we can do this very quickly now. There's 8 advertisements we have to arrange, and we know that the number of ways to arrange 8 objects is 8 factorial. 40,320 ways to assign time. So, some questions might require us to use the fundamental counting principle, but questions where we're arranging a bunch of distinct objects, we can now use factorial to make our life easier. Having said that, the number of ways to arrange n objects is n factorial. So let's think about what 0 factorial might be equal to. So this is equivalent to asking, how many ways can you arrange 0 objects? Which might seem like a silly question, but there's actually an answer to that. How many ways can you arrange 0 objects? Well, there's one way. You don't arrange them. You don't arrange any. There's just no arrangement. There's no objects. 0 factorial is actually equal to 1. You can verify that for yourself on your calculator as well. So moving forward, we can use factorials to actually solve more complex problems. So here's an example where we tie in the indirect method. So let's say I've got a really talkative, rowdy grade 9 class. And I've got 7 students in the front row. I want to put all the chatty kids there. How many ways can we arrange all these students? Well, we know how to answer that quickly and efficiently now. If I'm arranging all 7 in the front row, that's just 7 factorial, which is 5,040 different ways that I could arrange all the students. That's the total number of arrangements. Now let's say that I was concerned about a couple of students who are maybe best buds, really talkative. Like they cause even more trouble when I put them together. Let's call them Bert and Ernie. So how many arrangements of those 7 people are there when Bert and Ernie are sitting side by side? In a question like this, where we're treating 2 of the objects as being like together, our strategy is we're going to take Bert and Ernie and we're going to treat them, this is the key, we're going to treat them as one. If we treat Bert and Ernie as one person, well, then you have 1, 2, 3, 4. Remember, we're treating Bert and Ernie as one person. 5, 6 objects to arrange. So instead of arranging 7 objects, we're arranging 6. So 6 factorial. That's not quite all there is to it, though, because keeping Bert and Ernie together, there's actually 2 ways that can happen. I can have Bert and Ernie or Ernie and Bert. And I have to consider that for all these 6 factorial options, I can have Bert, Ernie, or Ernie and Bert. So we multiply by 2. I'm going to put 2 factorial, because if we were keeping 3 people together, there'd be 3 factorial ways to arrange them. So again, that 2 factorial is because we can have Bert or Ernie and Bert. And now we can evaluate this. 6 factorial times 2, 1,440 ways to keep these 2 guys together. And now we can answer the question, how many arrangements are there so that Bert and Ernie are apart, so that they can't be side by side? Well, this is actually pretty easy for us to do, because if you think back in part A, we got the total number of arrangements. And part B, we got the number of arrangements where they're together. That was 5,040. And number of ways of together was 1,440. And if we think back to, like, this is a connection to our probability unit when we talked about the complement of events. Like, either Bert and Ernie are together or they're not. If you consider trying to find the number of ways they're apart by using cases, it actually gets very complicated. You have to consider, well, what if Bert is here? Then how many ways can I arrange everybody else so that Ernie is not directly beside him? Well, there's only one spot that's a trouble spot. It's right next to Bert. But if Bert was in the middle, well, now you've got 2 spots that Ernie can't be, and how many ways can you arrange them on either side? There's a lot of cases, and it gets complicated. One way to make it less complicated is to use the indirect method. So please make the indirect method part of your math toolbox for solving counting problems. Why don't you try this one very quickly? Very similar question. 6 team photos hanging outside of a gym. 2 of them are the junior and senior basketball teams. How many ways could we arrange these pictures so that the 2 basketball pictures are separated? So if you want to pause and try that, you can unpause in a second once you're finished to check your answer. Or you can follow along with me right now. So we have 6 team photos. 1, 2, 3, 4, 5, 6. Remember, if we want to find the number of ways that they're together, we treat 2 of them as 1. So I might just write, this was helpful for me for the last one. The number of ways they're apart is the total number of arrangements minus the number of ways that they're together. The total number of ways to arrange 6 pictures is 6 factorial. 6 objects, 6 factorial. The number of ways to keep them together, using the same logic as the previous question, you treat the 2 basketball pictures as 1. Now you're only arranging 5 objects, but we could have the junior then senior team or the senior then junior team. So there's 2 factorial ways that can happen. And we can go to our answer now. 6 factorial minus, so you can double check that. There are 480 ways to keep them apart. So now we have 2 examples of using the indirect method. Let's switch gears a little bit. Let's revisit the fundamental counting principle. Can you do these 3 problems using the fundamental counting principle? And you might see that they all involve similar calculations. So if you want to pause the video, try these 3. Unpause when you're ready. But here we go. So 10 students in a student council. How many ways could we have a president and a vice president? So setting up the FCP, there are 10 students that could be president. After we choose a president, there are only 9 students left to be vice president. And that makes 90 different arrangements, 9 different ways we could choose a president and a vice president. In part B, if we add in another position, a secretary, so now we have president, vice president, and secretary, 10, 9, but now we have a third option, so that's 8 people left for that, and that gives us 720. And going one step further, maybe you see the pattern here, principal, vice principal, secretary, but now if we need a treasurer, we just continue the pattern, 10 times 9 times 8, but now there's only 7 people that could be treasurer. That gives us 5,040 options. These kind of calculations occur often enough that they have their own special name as well, called permutations. When you're arranging all the objects in a group, we use factorial. But in these calculations, we're only arranging some of the objects from a group. And so the new notation we have for these, what we call permutations, is the following. So what we just did in the previous, I'm going to use part C as an example. The number of ways to arrange 4 people from 10. Just going to write it out there. 4 people from 10. We say is 10p4. Another way of writing that is capital P 10 4 in brackets like that. And from our previous work, we saw that that is 5,040. The number of ways to arrange 4 people from 10 or 4 objects from 10 is 5,040. You guys will have a button on your calculator for permutations, or you should. It might look like NPR, most of them do, but it may also look like PNR. But yeah, 5,040. So this is the number of ways to arrange a certain group of objects from a big group of objects. Formally, a permutation is an ordered arrangement of objects selected from a set. The number of ways to select R objects from a group of N objects is given by N factorial over N minus R factorial. I'm going to throw on the notation there, NPR as well. Maybe just talking about an example we looked at earlier. Maybe if we look at the part B of that student council question, where we're having 3 positions, that would be 10p3. So let's talk about the formula and why it works, and maybe some helpful shortcuts to think about. So 10p3, using the formula, is 10 factorial over 10 minus 3 factorial. That is 10 factorial over 7 factorial. And using the skills we learned earlier at the start of our lesson, you can write 10 factorial as 10 times 9 times 8 times 7 factorial. And you can see what you're left with is the same calculation we got using the fundamental counting principle. Look, we get 10 times 9 times 8, which is what we get when we set up and use the formula. So we get 720. Another way to evaluate things like 10p3 by hand is to set up 3 blanks. If it's 10p3, you're going to start with 10. You're going to have 3 blanks. And again, we're kind of talking about a shortcut for doing 10p3. And then you just kind of count down by 1 each time, and you get 10 times 9 times 8. Now, to be clear, you guys will always have a calculator, and it would be for the best if you just got really efficient and just, if you recognize, oh, I only need 3 objects from 10, I'll do 10p3 and I'll go directly to my answer. That's ideal. But it is good to know where those answers come from. It comes from doing 10 times 9 times 8, 3 multiplications, and that as a formula looks like n factorial over n minus r factorial. So let's get a couple examples in here. It'd be great if you tried these by hand and also using a calculator. So I'm going to use the formula. So we're doing 10p5 here, 10 basketball players, 5 different positions on a basketball court. So 10p5, by using the formula, that's 10 factorial over 10 minus 5 factorial. That's 10 factorial over 5 factorial. And using our trick from earlier, that's 10 times 9 times 8 times 7 times 6 times 5 factorial over 5 factorial. That's just using the definition, the formula itself. What you should notice is you get the exact same answer as you with the FCP. 10 options for position 1, 9 for position 2, 8 for 3, and so on and so forth. And you also would get that answer by using the trick of 10p5, make 1, 2, 3, 4, 5 blanks, start with 10, and take it down. Of course, I would love if you guys just got to the point where you could do these quickly and efficiently in your calculator. Give that a try. 10p5 should get 30,240. Try the next one to finish things off for today. Maybe try setting it up by hand first and then try it on your calculator. If you want to try this on your own, pause the video, unpause it when you're ready. Otherwise, here we go. So we have 12 athletes here, and they can prizes or medals are awarded to just the top, that should be top 3 finishers. So you get a gold medal, or gold, silver, and bronze. So of the 12 people, we are selecting 3 and arranging them specifically in an order: gold, silver, bronze. Setting up the formula, that's 12 factorial over 9 factorial. Using our trick, it's 12 times 11 times 10 times 9 factorial over 9 factorial. And you get the same thing you'd get with the FCP or by using our trick. 12p3, 3 blanks, start with 12, tick it down with 3 numbers, and you get 1,320. So please make sure you try 12p3 on your calculator. Verify you get 13 and 20. 1,320. Maybe before we finish, just one interesting thing. Would you try doing, let's just revisit. Can you do 5 factorial? See what that is. And then I'd also like you guys to punch in 5p5 into your calculators and see what you get. 5 factorial, if you've done that quickly, is 120. 5p5, if you do that as well, you're also going to notice you get 120. Why is that? Well, remember that factorial is the number of ways to arrange n distinct objects. So 5 factorial is the number of ways to arrange 5 objects. 5p5 is saying how many ways can I arrange 5 objects out of 5 objects. It's actually the same definition as factorial. So in general, the following actually is always true, that n factorial is equal to npn. That always works. All right, guys. What's next for you is I've put up quite a large list of a PDF of practice questions. Try as many as you can. A lot of those questions can be done very quickly with one calculation. You really need to get a lot of experience solving problems in a lot of different contexts. After a while, you start to recognize, hey, this question is like this scenario and this one is like that scenario. But you do need to practice to get that experience to make them, they just get easier as the more you practice. I've also attached a link to a YouTube video just presenting these ideas, in a similar way, but with other visuals, and maybe sometimes just having a different voice go over things can help things connect better. So no quiz for today, no assignment for today. Just try to do lots of practice. And as usual, please let me know if you need a hand. I would love to help you. All right, guys. Hope you have a great day, and we'll see you online.